Afternoon. We have Ian, who'll talk about adventures and findings in ISP hacking. As a reminder, please put all your questions in Slido, bsidesSF.org/Q&A. There will not be an in-person Q&A, so if you have questions, that's the best place to address them. With that, thank you. Ian.
Thank you, everyone. So as I was mentioned, I'm Ian. I go by Landrat on social media. I blog about things like this and other many things at landrat.com. I'm an offensive security engineer on a red team. I run the BSidesSF network. It's like the Wi-Fi some of you may have been using. I run my own hobby internet service provider for fun. And I run a historical DNS database at dns.coffee. This talk is about none of these things. I'll be covering some security findings and methods used on 2 different Bay Area ISPs that I looked into over the past few years. And while not a traditional supply chain security talk, I will be talking about how some really basic vulnerabilities can be hidden within an ISP's network and how they can impact you as a customer or a business that might be downstream of them. So without further ado, the first ISP, Pigsplain. This is a local ISP whose name I've altered for the purposes of this talk. That'll become apparent later. So it all started when the internet went out. Nothing motivates me more than something getting between me and a functional internet connection, especially when stuck at home. And this was mid COVID pandemic. So with no internet access, I ended up checking my firewall rules and noticed a lot of inbound traffic on the WAN port from private IP space. This is RC 1918 space. It's like, what you traditionally see in your home network behind NAT, 192.168, 172.16, like 10 dot networks. You shouldn't be seeing this over the internet. It's not routable. I was curious, why was my home's router receiving these broadcast traffic? Some was broadcast, some was not, from this internal IP space, especially since my ISP did not use carrier-grade NAT. So I added an interface or an IP address on the interface on the WAN port of my router in these subnets, so I can start actually interacting with these subnets, send my own packets and see what's there and do a network scan. And I ended up finding a lot of the ISP's internal switches and routers. This turned out to be their control plane. There were no VLANs. So for those who may not know, what is a control plane? This is the default network within the network's infrastructure. It contains most of their management interfaces. It's used for things like SNMP, IBGP, stuff like this. It should be very privileged, no user data. It's usually used to admin or configure the network, and ideally should be logically separated from other networks, including user networks. So this is kind of an outline of how a typical ISP might set up their network with a control plane and VLANs between various customers. You have a different VLAN per customer, so they can't talk to each other. In the ISP modem, like your home modem, would be the edge of their network. The ISP can't get into anything beyond that, and you have no access to anything beyond that into the ISP's network. The control plane network allows for the ISP's engineers to access the management interfaces of all their routers, switches, etc. And again, they can reach into your home modem, but nothing beyond that, because normally the ISP owns that modem. Nobody else should have access to the control plane network, especially the customers. And depending on how it's configured, routers on the network, on different sub-networks between them, can selectively choose a route between them and chooses to pass traffic through. But that's all software defined in firewall rules. So this was this network. As one giant flat network. The DHCP server would only issue leases for the WAN subnet, like the internet. So you'd plug in your home router, you get an IP address, you can route, and it just works. But it's still all just flat. This is in my opinion, a very bad network design. And lots of modern network gear is very talkative. It would send lots of broadcast packets along the control plane, trying to auto-discover other switches, other routers. And it's also polluting the customer's network. If you're on a WISP or a limited bandwidth connection, all these packets are consuming up your bandwidth that you're paying for. So you're getting slower internet. So this is what I did, like we mentioned earlier. I just added an IP address on my router here, saying it by the top right one here, on that theoretical interface, and I can start interacting with that traffic by manually adding this IP address. And you use tools like Nmap and see what's where. So this is what I ended up finding. Found lots of internal services, SNMP, NTP, SSH services, Telnet, web servers for all kinds of internal devices, and all accessible through the control plane. I also found you can use the default gateway on the control plane and just get internet that way. Then you're basically opting into carrier-grade NAT, but it's not via the normal path for the internet. So you kind of get anonymous internet access because you're not using your WAN IP, you're using the ISP's WAN IP address to get internet access. We started interrogating a lot of the devices found. You can see via the HTTP responses or by the banners in Telnet or SSH what types of devices they are, what types of routers or switches, what model numbers. Some of these devices have default credentials. Some of them worked. Some devices had no authentication at all. Some had authentication, but those weren't as interesting. And of course, SNMP scans will kind of tell you what interfaces on what switches are plugged into other interfaces and how the bandwidth flows throughout the network. So you get a really good kind of like a virtual layout of like where the network is, or logical layout. Additionally, one particular switch allowed guest access, read-only access to the whole switch. Not that bad, but one interesting thing is the guest access has the ability to dump the config. Then the config contained the admin password in plain text. So that was exciting. I started Googling for some of the MAC addresses of some switches found, and I found forum posts of employees of this ISP posting their entire switch configs on various forums on the internet asking for help with different things. So I have 2 screenshots of it here. I added these redactions. They're not redacted at all online. These configs contain their passwords of admin users, IP addresses, even like their own corporate office wireless credentials are in here, all kinds of other stuff, and the firewall rules. I didn't test any of this works. I just saw them. I don't know how old it is. So at this point, I have a really good idea of how like the network is logically laid out. But let's talk about like a physical layout. This is an ISP that spans the whole Bay Area. Let's try to figure out where are these switches physically located, which buildings, or talk to which other buildings. So, like many home ISPs, they run their name server, and you can use reverse DNS, which is a DNS PTR record, to resolve an IP address to domain name to query it. So, by querying their name server for the IP address on the control plane of these devices, I'll get back their internal host name, and they're like the format, location dot type of device dot their domain name. So I can start doing this for every device I found, and it would tell me like they put like the building address it's located in the reverse DNS. So I can start actually physically mapping them out, which routers talk to which other routers and which ones are linked out. It gave a really good physical layout of the entire network map. If I work for another ISP, not kind of my hobby one, so you're really good for competitive intelligence. This is one of the theory I had. I didn't actually test this, but this ISP gives you a modem, like you'd expect, and the authentication for the modem into the network is done via the modem's MAC address. The modem's MAC address is stored on an SPI flash chip, pointed to by the little arrow right there, that you can just dump and rewrite. And I found my MAC address. I guess it's in that slide right there. It's at office at location 24. You can change that based to any other MAC address, and their network will think that you are that other device. So say you get onto their network, do an ARP scan, get the MAC addresses of all the other customers, clone any of those, you now get free internet that way. Of course, you still need the hardware, but you can buy that on eBay. It's not that hard. So for the disclosure of this, like I said, this is during the pandemic. This is information that's a few years old already, but I usually find these like in early August. I started discovering a lot of these. I emailed their support with some of the high-level findings, trying to disclose to this. I don't hear back from them. I sent some follow-up emails over the next few months. I don't hear back from them, or they said they're going to forward the network team. Eventually, I meet one of the lead engineers at a local Bay Area meetup. I tell him in person, and I'm kind of paraphrasing him, but like as long as the internet works, they don't really care. It all started when the internet didn't work, but that issue was resolved. So I don't know. Do it that way you want. Here's the second ISP, Sonic. They're in the Bay Area, and I highly recommend them. I've since moved, and I use them. Sonic is great. So Sonic if you're lucky enough to have Sonic Fiber, they give you an ONT. It's an optical network terminal, converts fiber to Ethernet. This is what the gigabit fiber modem looks like for Sonic. It uses the GPON standard. The particular one that they use, or that I had, was the 80tran 411. Does gigabit GPON. It also does VoIP and has a MIPS CPU. And you see how there's the physical characteristics of the device. As a Ethernet port, a phone port, power port, fiber port, and you can see the inside. There's a big heat sink, and there's one little header sticking out the side of it that's actually just for a UPS. There's nothing interesting on there. So first thing I want to do to learn more about this device is to try and find a UART serial console for the device. So as you get logs and possibly more, and to interact with the device at a very low level. To do that, 3 pins are required. You need ground, transmit, and receive. You can identify ground pretty easily with a multimeter by finding like some shielding somewhere at the negative end of the power and looking for 0 ohms from any of the debug pins. Transmit can be a little more difficult, but it's usually identified by fast fluctuations if the device is transmitting anything between 0 and 3.3 volts. Ideally, though, you want to attach a logic analyzer to a lot of these pins and look for async serial output and decode that in ASCII and look for something like this. So this is a screenshot of like the SAILI program, which is what I use, just like what the UART would look like output for the hello if that was to be reprinted. You can use the timing differences between the peaks to figure out the baud rate too. But there's usually like 2 or 3 common ones. You try those and move on if you don't get anything. And the RX pin won't output anything, but it'll most likely be like literally the pin next to TX almost always. And it's important to remember to connect the TX to RX, RX TX for whatever UART adapter you're using. If you connect TX, TX, RX, RX, nothing's going to work. So in this case, UART was identified on a hidden 4-pin connector you may have not noticed in the prior slide. You can see the pin out here. I'll figure out TX, RX, 3.3 volts and ground. And amusingly, this actually can be accessed externally. You don't have to take the device apart by pushing like little wires through the air vent holes, and you connect right to it. But now we can read the boot logs, and we can learn that the device uses the U-boot bootloader, which is really common on embedded electronics, especially ones that run Linux. And this device does run Linux. And after we see all the boot logs when it boots up, and when it's done booting, we are presented with the login prompt, and can't go much further than that. So the next step is, let's get past this login prompt. So the ideal way to do this is to desolder the NAND flash storage and dump it with an external NAND dumper. There's a little risk, though, to damaging the device when desoldering and resoldering, and at the time, I didn't feel like taking that risk. So instead, I decided the very slow and hacky way. So I used UART to enter the U-boot menu, and the U-boot bootloader has a few commands that are of interest here. So we have one command that lets you take all of the NAND flash, I think this one was 120 megabytes, and just read it all into memory. You give it a memory address for flash to read from, and a memory and a number of bytes to read, and a memory address and memory to write to, and it just does it. It's very, very low level. So I did that. Then there's another command to print the contents of memory as hex over serial. So I just issue that command. And then it prints as hex, and this is a screenshot of my laptop receiving that dump, both in code and hex, and then the ASCII representation over about a 115K baud serial. You'll slowly read out all the contents of flash as hex. This is incredibly slow. Once you get this file, you can use programs like screen with the -L to log the output of the serial output, grep, sed, and xxd to reconstruct it to like an actual binary with the flash dumper would have actually given you. Doing this on 120 megabytes, doing it this way, took about 15.5 hours to actually dump. So a normal dumper would take maybe a minute or two. So left it running overnight. There's also a tool called BCM CFE dump that is meant for the same model of CPU that's in this device that will do this. It automates the process. It's not any faster. It still takes 15.5 hours, but it just means you don't have to use like a bunch of shell scripts to reconstruct the binary. It just does it for you, but it's still incredibly slow. But now we have a flash dump. We can try to see if we can find find anything interesting in there. So the file system has a bunch of partitions, and you can see here, this is the top screenshot is from the boot logs to see what the various partitions were, and we have the offsets into them. There's no partition table like you'd have on your normal computer, like GPT or MBR that does this. We have to, just know the actual offsets in the file system, and we have those now. The most interesting one, the root file system, is JFFS2. And we can pull that out using the dd command, just literally set the start offset and end offset or number of bytes in these dumps and create a new file, and then extract, the JFFS2 file system and extract a local directory in your system to look through and see what's interesting in there. Of course, the first thing we want to look at is etc password, see what users exist. Found 4 users, admin, support, user, and nobody. The interesting things here are these users, or this is a step using just MD5 for the hashing of the password, which is not that great. Also note, I looked in Etsy group. All of these members, even nobody, is a member of the root group, GID0. So they're effectively all root. And there's on the slides, there are 2 links to online MD5 hash cracking services. 2 of these users, their passwords are found instantly. The MD5s are known. The user password was user. The support user's password was support. I am a bit embarrassed that I didn't guess those. Yeah, next time I should try a little harder on that. The admin and nobody users weren't found that way. And also just interesting note here, why does nobody have a password? The nobody user should not have a password, should not be allowed to log in. Why was it shell bin sh? Also, there's a comment there saying it's for FTP. That kind of makes sense, but then it still shouldn't have bin sh as a shell. So the FTP user can log in as, and get a shell in theory. But let's move on a little bit. So also in the boot logs was a strange message here about CISRQ. I had never heard of this before. It stands for System RQ. I don't know if anyone else has ever heard of it, but there's this button on your keyboards you may have once seen that literally says the same thing. So it's called the magic CISRQ key. It's a key combination understood by the Linux kernel, which allows the user to perform various low-level commands regardless of system state. So you can do things if the kernel freezes or like when kernel locks up, you can do this magic key combination with that key and basically start debugging your kernel. It's meant for kernel development. I'm really surprised that they actually dedicated a keyboard key for this. You won't see it in your laptop, but it's on like full-size keyboards. So how does this work? Basically, you type, Alt, CISRQ key, and then another key, and it does an action based off what that key is. This is a screenshot Wikipedia of some. There's lots of commands and actions you can have it do. But one of the interesting ones, you can send a sigkill to the PID1, which is an init system, and that will almost always just drop you to a root shell. And this device was that enabled, so I can just boot it via the serial console, send this key combination, and it just gives you a root shell, and that works. But no, I was accessing this over the serial UART, which doesn't have like an actual keyboard. It just sends like UART commands, and I was using the screen terminal emulator. So for that, it's a little different because there is no, the CISRQ will get interpreted by your computer, not by the computer that you want to pass the over serial. So you have to use everything on the slides. It's like Control A, Control B, and then the command key. You don't actually use the CISRQ key here. That was way off. The first way, actually, I got the root shell. I haven't actually even needed the passwords yet. But also in the boot logs, the device, we have its IP address. It does boot up and show it has an internal local IP address for you to access locally if you need to debug it. It happened to be 192.168.1.1. You can do an mmap scan of that, and you see it's running a telnet server and HP server. So now if you set the computer you plug directly into it, its IP address, like say 192.168.1.2, you can talk directly to it, interact with these services. So I started taking a look at those. The telnet interface drops you to the exact same login prompt as UART, although now we have the passwords here, so we can log in. It's a very limited custom CLI. It's not a normal shell. There's no shell access, but it has access to a few normal shell commands like ping. It's meant for network diagnostics. Can we escape this limited shell? Of course, the answer is yes. So see how this auto plays. Yes. So the ping command allows for a command injection via a semicolon. Watch it go in. It's like I'm logging in as user. You can see all the commands that are available here. So I'm tempting. Can I do sh? Can I do bash? Nothing's working here. But we have access to ping, and this looks just like the normal ping output that you'd have at your system. So I know it's not like interpreting ping. It's actually just calling the actual ping binary. You can ping yourself. Can run bash. I have to ping myself again, but then it drops you a bash shell. And so what's really interesting here, though, is this is surprising. It actually works with a full encryption interface. So you can run interactive tools like VI, top. I didn't expect that to work. No tab completion, unfortunately, that did not work. But there's an Etsy password. This is my favorite part here. When you exit it, it tells you to have a nice day. I love the fact the engineers put that in there, but didn't fix the command injection. All right, so moving on from that, the web interface is also accessible. We can log in, I guess, in the same credentials we have. We just have the user and support users. But it's very limited, again, what we can do. It's like read-only access, can't see many interesting details here. But when you go on the password change website, it mentions there's a lot more features available as the admin user. But that's, we don't have that password yet, so we can't see what's there. But I did find some of the web interfaces, even for the guest user, have some very interesting features on it, such as you can enable mirror ports, which could enable a local LAN tap. Again, not remotely, but locally. It's probably meant for engineering debugging. But one of the most interesting is you can do a packet capture, and this does just shell it to TCP dump. So the network engineer can do a packet capture of you, or assuming they're trying to debug a session or fix something, which is I consider very privileged for a non-admin user. And much like the telnet-like interface, there's also a ping utility. It does not support command injection via a semicolon, but it supports it a different way. If you open it basically in two different browser tabs at the same time, and you can send a command, and by default it just says command equals ping. You can change it to whatever you want. In this case, I just did cat proc CPU info, and another command tab. You can refresh the output of that, and here's the output of the CPU info page. It's going to do the architecture, so you can see what you're running on. It does require two different requests, but it's still command execution. And remember, the web server is running all users, but including the web server is running as root. So this is root command injection here. There's also now we have the file system dump. I can look through where where the web directory is being served from, and there are a bunch of pages that aren't linked to, these hidden web pages. And one of the very interesting ones is dump sysinfo.html, which creates like a debug dump of the entire system. The non-admin user, the user can't access this. We can create this information dump. Let's go do that. We'll click the dump, takes a minute, open up the file. It's a very large XML file, and dumps all the system passwords in plain text. We now have the admin passwords. Yeah. See anything? Yeah, there's also dumped another user that wasn't password. It looks like manufacturer user whose password was manufactured password. It also contains other things like all the SIP server configuration and the SIP password too. So if we want to access their control plane, we can run our own SIP service if we want to. If we don't want to use their ONT. So speaking of the control plane, now I'm actually logging in as root or the actual user this on the shell. We can see all the network interfaces on this device. See here, the main interface, the main bridge interface, BR0, is the customer-facing internet connection. This has the 192.168.1 interface on it. We can also see an IP address on a VLAN 702 on the GPON fiber interface in the 10.8.128/19 interface. This is a huge subnet, over 8,000 IP addresses. This is their control plane. We're now on the control plane, similar to what we had in the very first ISP, but no hacking required this time. Or sorry, some hacking required this time. I was able to confirm with some other friends of mine who had the same ISP that we could ping different devices through this control plane behind the ONT, which also means that these modems are routing between the customer's network and the control plane for certain types of packets. So you can ping parts in the control plane, but not talk to them much. On all network services, like the telnet, web server, we're listing on all interfaces. So they're listing on the control plane and the user's interface, which is what I was asking from, which is probably intentional. So, like say the network administrators need to debug something, they can access it via the control plane, get access to the same web interface or telnet CLI that I was accessing remotely. So this got me thinking, does this mean that, one compromised ONT, such as mine, could, on the control plane, get code execution on another customer's by accessing its debug interfaces over the control plane? If so, they could literally have a man in the middle, like someone else on their network, and lots of great network debugging utilities are pre-installed in here, like TCP dump, for example. So I did end up disclosing this to Sonic because this was, as a customer, I wanted this not to be done to me, and I wanted it to be fixed. They are very receptive, and they actually gave permission for this test. That was what I was really after because I don't want to actually do actual crimes. So they get a test in lab environment to test this. They were also really eager to see if this would work. Fortunately, this did not work. Their system was configured in a way to block ONT to ONT communications, basically at their router level. So even though it does route, you can talk to only infrastructure on the control plane that isn't other customers, which is great. But like I mentioned earlier, you can still talk to other things on the control plane, like their gateway, DNS server, and the VoIP servers, and maybe more. I didn't explore that too much. So as I mentioned for disclosure, this was a much quicker disclosure timeline, at least for disclosing them to acknowledge it and work on a fix. First off, I want to say that none of these findings were Sonic's fault. They're all in the bugs in the firmware of the hardware device manufactured by ADTran, who I initially tried to disclose to twice. They're not very receptive because I am not a customer of them. I have no relationship with them. So I disclosed to Sonic, who then pushed ADTran to actually release a fix, and they did. They initially pushed the fix just to me. I tested it. The fix basically just cut off the telnet and web server interfaces and just turned off the UART interface on the device. I don't know if these interfaces are still enabled on the control plane. I guess they are, but I don't know that. But that basically cuts off all user access to that without finding another vulnerability and effectively mitigating all these vulnerabilities, which is great. So this is a security success story. There were 5 CVEs issued for these findings for the ADTran ONT. One other comment I want to throw out there, when I was looking through the firmware on this, there was a lot of references to other hardware that ADTran makes, other types of devices. So I wouldn't be surprised if these same vulnerabilities might be in their other products. I'd hope that ADTran, when they receive this report, both for myself and Sonic, that they would look through their other products and make sure that these issues are also solved, but I don't have any other hardware. I have no idea. So some of the takeaways and impact from this is, all the web vulnerabilities I'm showing you all here are very basic stuff, like simple command injection or really, really simple guessable passwords. It was very worrying to find these, but these are really, really low level stuff, and this stuff's still out there today. It's affecting lots of people, and it's going to affect your network, your business network, if this is the type of stuff you're relying on. I'm not trying to say everything is bad. I'm trying to say that these still look at embedded stuff. These rules, knowing how to look at these embedded systems can, in combination with these basic vulnerabilities, can be very rewarding. You can find a lot of vulnerabilities and hopefully get them fixed. That's hopefully a good success story. And that's my talk. A version of this will be posted at my blog, landart.com, in a few days, hopefully. That's all. I think there's questions on Slido. If you have any questions.